Tonight we have a guest to introduce this evening's presenter. It's my privilege now to welcome UAF Provost and Executive Vice Chancellor Anupma Prakash.
Thank you, Virad. Well, on this International Women's Day, it is my pleasure, absolute pleasure, to introduce Dr. Nettie La Belle-Hamer, a powerful and influential scientist. Yes, she is a scientist first and foremost, who's been a major mentor and inspiration to many women aspiring to be a scientist and a leader. Dr. Nettie La Belle-Hamer was named UAF's Vice Chancellor for Research in January 2022, after she'd served in interim service capacity since May 2020. And the role of the Vice Chancellor for Research is to build capacity and depth in UAF's research and development efforts. And she does that with gusto. In becoming the Vice Chancellor, La Belle-Hamer stepped down as the Director for the Alaska Satellite Facility, a position she held since 2002. And under her leadership, the satellite facility grew and expanded, and it provided access to remote sensing data and tools for the users to use that satellite data. La Belle-Hamer served as UAF Geophysical Institute's Deputy Director from 2015 to 2020, and UAF's Associate Vice Chancellor for Research from 2011 to 2015. She managed the Science Center before that, and was employed by a private company working with ASF in the 1990s. So she's got a long and cherished career here at UAF. She's a lifelong Alaskan. She received her bachelor's degree in physics. Yes, she is a physicist. And that was from the University of California at Berkeley, and her master's degree in space physics at UAF. She worked at GI, that's the Geophysical Institute, research assistant from 87 to 94, and she earned her PhD also in space physics from UAF. She's got many awards, but here is something right out of the press for you. Dr. La Belle-Hamer's most recent and prestigious award is the 2021 NASA Exceptional Public Achievement Medal, which is awarded to a non-government person for sustained performance that embodies multiple contributions on NASA projects, programs, and initiatives. And I want to read out this. Here is what her letter said. Her dedication in the role of leader in SAR science data systems and curation will make a difference for generations to come. Nettie's 2+ decades of drive, dedication, and lasting contributions to NASA's mission and the broad community of SAR data users is the embodiment of public service and made her a natural and deserving nominee for NASA's Exceptional Public Achievement Medal. And here is what Dr. La Belle-Hamer had to say. She said, I am deeply humbled by this prestigious award. When I read the email notifying me, I was so stunned, I didn't move for 30 minutes. This is such a huge honor and reflects not just on me, but also on the whole ASF team. What a great statement by Dr. La Belle-Hamer. And when she is not busy giving a lecture or a science talk and promoting UAF research, you will be able to find her somewhere, maybe running a marathon or dropping a puck and cheering the Nanook hockey team, or more recently, just spending time and playing with her granddaughter. So thank you, Nettie, and the floor is yours.
Thank you very much, Anupma, for that amazing introduction. It's always a little bit embarrassing to hear about yourself in such a way. And yes, I really did sit there for 30 minutes, just in case you were wondering. Thank you for coming tonight. I'm excited to talk about one of my favorite topics, the Alaska Satellite Facility. And we have indeed been dishing it out for 30 years. I just recently became the Vice Chancellor for Research, so this title slide for me was difficult because for the first time in over 20 years, I did not have ASF Director on my title slide. So today is a new day for all of us. We are talking about history today, but I'm just going to start out by saying I am no historian. I am a scientist through and through, so I'll do the best I can. So that means ASF can be put onto, the history can be put onto one slide. We were established in 1991, and we'll get into the replacement of the first dish here in a minute, but the second dish was called AS1, was installed in 1995. Then we had their third in 2013, and our fourth came along very recently. In 1994, ASF became a NASA data center. And this is a really important part of the character of the facility. We will talk about that as well. I became involved with the Geodata Cooperative. It's something that we created through a partnership that came through ASF. And we put in the contract as late as 2020. And today, instead of going through a lot of history, I actually want to talk more about the story of why. And we're going to talk about why Fairbanks, Alaska, why synthetic aperture radar, why is there ever evolving technology that we have to constantly learn something new? More importantly for us here in Fairbanks, why UAF? And so rather than go through a lot of history in detail, which I'll try to get to, but honestly, really what I want to do is tell you a story. So what's the best way for me to do that? Well, let's see. I think this has been done before, so I don't really want to do it this way, although this was a really good story. Let's try something else. Let's start in the beginning. For us, that was in 1982. And no, your screen is not blurry, but my memory kind of is. 1982, NASA formed a small working group to look at how could the US science community get access to some of the most important data that was coming out in the world right about that time. There were 3 satellite missions that were planned to launch in 1988, and we wanted to be a part of that because all 3 of those missions were not US satellites. So how were we able to do that? So the Alaska SAR facility was born from this working group. It was a joint science proposal between JPL scientists and UAF scientists who proposed to NASA that we could gain this access to this very impactful data. How do we do that? And so let's look at how that started. But the first question really a lot of people ask me is why Fairbanks? And so I can tell you why Fairbanks by looking at these circles. If you look at the red circle, that's a polar orbiting satellite orbit around the Earth. And as you see, it's a low Earth orbit, very close to the Earth. Then we have medium Earth orbit. We're very clever with our names, low and medium. But then way out here, we have the geosynchronous. So the polar orbits travel north to south and take about 90 minutes for one full rotation. Sun synchronous, it is sun synchronous, which means it comes over the same part of the Earth about the same time of day each day. And then out here is the geosynchronous, which is what people are actually more familiar with, whether you realize it or not, because this is where the GPS satellites are, it's where the communication satellites are, and it's the ones that people usually interact with. But the ones that we interact with at UAF are these low Earth orbiting satellites. And it only takes about 90 minutes for the satellite to go around the Earth one time. So it's quite fast when you think about it. The geosynchronous orbits, by definition, take 24 hours to go around because they are looking at the same port of the Earth, geosynchronous versus sun synchronous. So this is an important thing to understand about the orbits before we get to the I will get to why Fairbanks, I promise. So if this is the ground down here, here we are in an airliner. Commercial airplanes fly about 6.6 miles above the Earth. And then you go up a little bit farther, this scale goes up to 100, and then right here, the Aurora Borealis is in between about 60 to 200 miles. Go up a little higher, the space shuttle orbit is about 300 miles above the Earth. We go up a little bit more, and there you are with the polar orbiting satellites. Those are the ones that we here at the Alaska Satellite Facility talk to on a daily basis, and they're at about 500 miles. Now, way at the top, and you can't see it because of the zoom thing. I don't know how to move that. But way at the top, very, very far out, are the geostationary, geosynchronous satellites, the communication satellites that I was talking about. And those are somewhere between 22,000 and 26,000 miles above the Earth. The difference is phenomenal in terms of where the satellites are orbiting. And we are here at Fairbanks, we are most concerned with those at about 500 miles away. Why? Why is that? There we go. So this is a much speeded up version of a polar orbiting satellite looking at strips of Earth as it goes around. And you see, it doesn't see the whole Earth all in one time. It sees it in strips. And this is an important part of how we work with our data. And the reason why it's important for us to be at high latitudes, I'll show you as we go. You can see that there's at the lower latitudes, there's places where it takes a long time for the satellite to ever see it, and at the same time, over the poles has been seen many, many times. This is really key to why Fairbanks. So if we look at it in a still picture instead, you can see the light circle that's around Alaska here. That light circle is what we call the antenna mask. And you can think of it as what we can see from Fairbanks. So from our antennas in Fairbanks, as the satellite comes over, if the ground track of the satellite crosses into this circle, then we can see the satellite, we can talk to it, we can give it commands, we can get data from it, and that's where our interaction is. And if you look over here, at the one that looks almost like a yarn ball, the black lines show how it overlaps, how the orbits go, and as it precesses around, there are many more crossings of our mask in the northern hemisphere. Then, if it comes down here, if we say are in the lower 48, you don't see as many. You don't see the satellite as many times. So back to the history. Remember, that most of what we just talked about in terms of why Fairbanks is really about the ground station. It's about the equipment that we use to talk to the satellites as it goes over. But ASF is more than a ground station. In 1994, in the midst of all of the antennas that were coming in, ASF became one of NASA's distributed active archive centers. And this is a really important part of who we are and why we're so much part of the national science scene and the international science scene as well for NASA and for synthetic aperture radar. We are trusted data stewards for NASA's National SAR Data Archive here in Fairbanks, Alaska. And that really started because we had the antennas here. So the antennas, in a way, anchored the data center to be here. But then as it grew, what also grew was our expertise and our ability to handle the data. So this actually becomes a really important part of the character of the ASF team. So as Dr. Prakash was saying earlier, we create tools to view and manipulate this complex data set. The software to generate higher level products, we help interpret the images. So as we start looking at synthetic aperture radar, we see that it's really specific, and it's important that we have developed the amount of expertise and knowledge that we have, that we share with the science community, not just about the technology of getting the data, but using the data itself. So if we look across at NASA's Distributed Active Archive Center, the green states are the ones that have a data center in it. And so Alaska is a really big part of the National Archive for NASA. And many of them, as you see, are clumped in the DC area. And we are, of course, the most physically far away. But there's a reason why we're here. And it makes all the difference for us. So that's why Fairbanks. But let's talk about why SAR. So this is a photo that I took out of my window when I was flying on Alaska Airlines. And this photo, more than anything else, shows why SAR. So when you use radar, you can see through clouds. When you use the camera, you cannot. The camera is very much like the optical sensors that are on satellites. So if there's cloud cover, what you see is the clouds. And if you're trying to look at the clouds, that's perfect. If you're trying to look at the ground underneath the clouds, not so much. So then comes in SAR. So let's take a minute for me to explain to you about SAR. I promise I won't take a long time and no equations. But let's talk about acquiring the data. Passive sensors, such as a camera or your eye, they record the energy that naturally radiates off of the object that you're looking at. For example, in this picture, the scientist is reading a book. Her eye is the sensor, the target is the book, and the light source is coming from her lamp in her lab, and the processing, the analysis that happens is in her brain, and from there she comes up with the application or an idea or another book, honestly. So that's a passive sensor. If the light was turned off, she couldn't read the book. That same analysis can be done with a satellite. So in this case, the sensor is on the satellite itself. The energy source to illuminate the target, which is the Earth, is the sun. And then we have the neural pathways go from the satellite through the antenna to the computers where you do the analysis, and then you create the idea or the application in the end. So that's a passive sensor. If the sun wasn't there, if it was night, you could not see. If there was something blocking the sun from hitting the target, you could not see. So in comes active sensors. And just like the passive sensors have a really common application of the eye, the active sensors also have an application that most people are familiar with, and that's sonar. So in sonar, the creature or the submarine, in this case, actually sends an active signal out, and so it supplies a source of energy, and then it records the energy that comes back. And in that comparison between what they know that they sent and what they know that came back, there's a lot of information. And you see this in nature, you see this with submarines, and you also see it with synthetic aperture radar. So in radar, the chirp sends out the signal, it hits the Earth and bounces back. How much bounces back compared to how much was sent is everything. It tells you so much information. But in addition to that, the satellite is moving. So as it's chirping, it's moving. And that movement is actually really important to the resolution of the data. We use that movement to create a bigger aperture. In a camera or in radar, the bigger the aperture, the better the resolution. And in this case, we're using synthetic aperture, which means it's not only the aperture of the sensor itself, but it's that aperture moving along in space. And so as it moves, the chirp that comes back to it is coming from, it's going to a different place, if that makes sense. So you're making a synthetically long aperture to get a higher resolution. So what does it look like? Well, it's beautiful, is the truth. This is a SAR image, synthetic aperture radar image, and the different shades of gray tell you how much data or how much of that chirp came back. The darker image means that the energy was radiated away. The lighter portions mean that it was reflected right back at the satellite. So then you get surface roughness, and you get a lot of detail at a very high resolution because of that synthetic aperture. Okay, so now I'm going to talk a little bit about the wavelengths just to give you an idea of why we're using radar. And so let's just orient you first to this graph. For those of you in physics, you've seen this many times. For those of you who haven't been in physics yet, I invite you to take a physics class. It's fantastic. But that being said, in this picture, I'm going to call this brown. I don't know what color this is. I'm a physicist, not an artist, so I'm just going to call this brown. And the brown portion goes from 0 to 100, and that's the atmospheric opacities. So think of it as the opposite of transparency. So it's opaque. Here at 100% opaque, you can't see through it. And down along here, you have the size of the wavelength of the energy, so the light that's coming in. And for us, visible light is right in this region. So in visible light, we can see through quite a bit of the atmosphere, but not all of it. And it's highly variable. But if you come over here to the radio waves, then the atmosphere itself is completely transparent to the radar signals. So that's why we use the radar when we're doing these observations with SAR. Now, I did promise no equations, but given that I've had so much problems with my computer already today, I think I'm going to break that promise, and I'm going to show you some equations. But I promise you, it's super easy peasy lemon squeezy. There's just a few things that we do to take the data that you saw and manipulate it into to the form that we can use as data. And so and there you go. There you go. That's science right there. So I know it looks like art, and it's beautiful, but science is beautiful, and so is this. I'm going to talk to you a little bit about what it is that you're seeing in this. So let's go back a few steps. That was my only slide with equations, I promise. The Cotopaxi volcano in Ecuador. This is a spaceborne SAR image of that region. And if we look a little bit closer at just this region, you can see what I said before about the backscatter being dark and light. You can see the different details in the surface roughness and of the volcano itself. But that's looking at only half of the data. That's looking at what we call the amplitude of the data. And because these are waveforms, they also have a phase. So the other half of the data we can use to create what are called interferometric phases. So this interferogram on the top is that region right there. And why is that important? If you look at the interferogram, you can see that the colors repeat. And it's like a contour map, really similar to a contour map. So if you go, say you look at the teal blue, and then you go to the next time the teal blue is, depending on the sensor, you know how far that is, and you can see the rate of change across that. And from space, we can measure down to the centimeter. So this is an incredibly dense, interesting data set where you can look at not only the backscatter that shows you a lot of the surface information, but then you can also look at the topography. You can look at changes. If you look at something before and after an earthquake, you can measure to the centimeter what the changes are, and you can identify where the area of most change is. It's incredibly interesting data. We can also do cool things like this. So this is the same data set that I just showed you, but now it's been rendered into a video. It has the information about not only the surface itself, but also the height because of the waveform and the differences in the wavelength of the signal that was sent out and the signal that was brought back. So this incredibly rich data set gives you information in a way that you really don't get from other types of data. So I am going to look at what else can we do with SAR, because that's one application. But honestly, there are so many applications of synthetic aperture radar in geoscience that it's useful for almost every discipline that you can think of. We can use it in geology. We can use it to study volcanoes. We can study glaciers. So remember, we do surface resonance, but we also do height and change. So it's good for hydrology. This is a north slope with some frozen lakes. We can look at fire scars before and after, because we can see through the clouds. It doesn't matter if there's smoke or clouds, we can see right through it. We can do seasonal studies, leaf on, leaf off type of work, and frozen, whether the water is frozen all the way to if the lake is all the way to the ground or not. I mean, there's all sorts of things we can do. We can look at human impact, which includes things like urban sprawl or deforestation. And we can look at sea ice, which is, of course, really important for not just for navigation, but it's important for the climate change studies in many, many different aspects. But we can also do a lot of work on open ocean and some of the waves that we see here. And sometimes what you really see on the ocean water is the imprint of the atmospheres like the clouds or the tornadoes or hurricanes on top of the water. So you get a lot of information about the ocean, but you also get a lot of information about the atmosphere. So it's an incredibly rich and dense, complex data set. But then why do we have to constantly do new technologies? I mean, those of us who have cell phones, we ask this all the time. Why is the operating system keeping changing? Why did they move? Where my icons are? Why doesn't the Mac work with the PC? All these questions, right? Why do we have to keep learning these new languages, new operating systems? And even at ASF, we've had to learn and develop new methodologies in order to do our work. Why is that? Again, brief history. I'm going to talk about downlink rates for the antennas that we have. So the satellites in the 70s, when they first went up, they had a much slower downlink rate. And as time went on, if you look at the difference as the new satellites were developed, the rates went higher and higher. And now we're looking at one coming in the future that's going to be the highest yet. Well, and if we put it on a plot versus time, here's time across the bottom, and here's the bits per second here, you notice that it's what they call a hockey stick, right? Where it's growing pretty steadily, and then all of a sudden technology takes off. Well, what does the speed have to do with anything? Speed is actually a proxy for the data size. So the faster it comes, the more data we have. So this hockey stick for the speeds of the satellites that are on orbit is almost exactly the shape of a curve for the size of the data, the amount of data we have. So in 1991, we started taking data here at ASF. And from 91 to about 2012, we accumulated about 1 petabyte of data. But since 2012, we have over 13 petabytes of data at ASF. So suddenly, it goes a lot faster, and we have more data. So a petabyte is a lot of data. And there are different comparisons, but my favorite one is that 1 petabyte of data, if you imagine 20 million 4-drawer filing cabinets filled with paper that are filled with text, that's 1 petabyte. We have 13 of those right next door in synthetic aperture radar data alone. And it's coming in 2024. NASA will be launching the new NISAR satellite that will, between the data that comes down and the data that we have to present or process and create for scientists, it'll be over 150 petabytes just over three-year mission for one satellite operation. So that's one sensor giving us more data than we've had in the last 30 years put together, by a lot. So that's why we have to constantly be looking at new technologies, new way of handling data, new way of making sure that the data are useful and in the hands of the science community that uses them. So I want to talk a little bit about the newest project. It's not a NASA project, but it is with the US government. It's called the Geodata Cooperative. And ASF is a very key founding part of this. And so what we say is we have ASF, which is .edu. We have KD Geospatial Solutions, a small .com company. Lockheed Martin, a not-so-small .com company. And GeoNorth Information Services, which is not only a small Alaskan company, but it's owned by the Titlik Corporation. So it's an Alaska Native-owned corporation that has gone into the IT world. And we're so proud that we're partners with them. They actually, GeoNorth actually has offices here right next to ASF, and we interact daily. So what are we working on for them? We're working on what's called GeoInt, which is geospatial intelligence information. And this is just a small glimpse of what it is that we're looking at. So I was showing you before how we have the black and white images, which are the synthetic aperture radar amplitude images, and then we have the psychedelic hippy-dippy stuff that is actually the interferograms that uses the phase. This is really one more step in terms of, actually it's probably about 12 more steps, but it's a little farther down the road where we're looking at the purple is just showing no change, and then where change has happened between the times that the two images were taken, it's actually a stack of images, it pops up in as bright colors so that you can immediately see there's change here, there's not change here. Why is that important? When you're mapping the entire globe, as the US government does, it's very expensive to map every single part of the globe over and over again. What if you could tell them, you only need to redo this piece because that's where the changes are? That's what ASF is doing. That's what we're doing for the US government. We're telling them where the changes are so they can look at those specific regions. So honestly, this saves the government so much money because they don't have to remap the whole globe in order to find the change. We tell them where the changes are and they remap that area. But it comes back to why UAF? Why? Well, you know, at first it really was about location, right? Location. But, and I need to stop here because I just see this picture. So this picture, this antenna, that was the original antenna. That's our first antenna that we had here from NASA. Its name is AS2, which is a long story that I don't have time for today. But AS2 is the one that you see now if you drove by this building today. Is not this antenna. We actually replaced it in 2017. So this is the original antenna. And it's become an icon. Who doesn't know the big blue dish, right? If you say, if we give directions to come to my office, I say, you go to the building with the big blue dish. Everybody knows the big blue dish. Here's the thing that's really cool about UAF. Nobody else has a blue dish. We're the only ones with a blue dish. The blue dishes don't come in blue. Dishes are white. So when this one needed to be replaced, it became an issue with the then chancellor, who said to me, if you're going to replace that dish, please make sure that it's blue. And I said, no. No way. I'm the first female director of the Alaska Satellite Facility. I am not going to go to NASA and say I care about the color of the dish. I'm just not doing it. It's too embarrassing. I'm not going to do it. So of course I did it. And then NASA was like, are you kidding? You want it to be blue? I said, okay, don't make me repeat this, but yes. And I said, it's okay if you say no, but the chancellor wants it blue. And they're like, no, it's fine. What color of blue do you want? And I'm like, I don't know. What color of blue do I want? I'll ask. And I asked the chancellor, what color of blue do you want? And he said, UAF blue. I said, well, that makes sense. And so I said UAF blue. So then, and we had to give him the color number, right? So then, it comes time, we have to go through a lot to get all the approvals, the design, everything ready. And so at the design review, NASA presented me with what we call the big reveal, okay? They presented me with this. So this is a poster that shows the blue dish and a pink dish, because they said, are you sure, you are a girl, are you sure you want a blue dish? Wouldn't you rather it be pink? And I was like, no, blue is fine. Thank you very much. So we ended up with the blue dish. It's UAF blue. The irony of that to me, not only the fact that I have a poster of a pink dish, but the irony to me was that the original blue dish was not UAF blue. The then chancellor insisted it be blue, but he wanted it sky blue because he didn't want to scare people with this big dish, and he thought it would blend into the sky. But you know what? It doesn't blend, and I'm glad it doesn't blend, because I love the big blue dish, and I love all of my dishes equally. So really, we're here at UAF because of location, but that's an old story. That's a 1988 story, that we came here because of location. Really, what I can say is we're at UAF because of the people. What we did together over the last 30 years was build the expertise, the knowledge, the ability to work in this highly technical, complex world. And we are so integrated into the NASA data systems that it's really, this is why. It's the people. And I love the people I work with. This is an amazing place to work. I highly recommend it. So see my earlier comment about take a physics class. It's awesome. But that's all I wanted to say for you tonight. I just wanted to say thank you very much for giving me this opportunity to talk about one of my most favorite subjects in the whole world, the Alaska Satellite Facility. We've been making remote sensing data accessible since 1991. Thank you.
Dr. La Belle-Hamer, thanks for that great presentation. And I like the blue dish. I do. All right.
I'm relieved it's not pink. That would be horrifying. Yes.
We do have some questions from viewers, and we can get to. I'm going to kick it off though, because one of your slides, I'm curious, how many satellites does the satellite facility draw data from, and are all satellites the same?
So the number of satellites varies in time, right? So it depends very much on what NASA wants us to be doing at any given time. So when we first started, remember I told you that there was going to be 3 satellites to launch at the same time? Well, as satellite go in this world, they did not launch all at the same time. And so for the first year, first 6 months, we only had 1 that we were dealing with, and then 2. And it took 5 years before the 3rd one was launched. And now we can handle, God, I want to say 13, 14 at a time. And so not in any time in day, but in that we service over the month or so. And we have we now have 3 dishes here on the Trothieta campus, the one that's on the roof that we talked about, and then 2 others in the woods. You can see them above the tree line. And NASA just last year installed the newest one, which is out on our North Pole site, the ASF Richardson site. And so once that kicks up, then we'll be adding more satellites to our regime.
Do they have different instruments on them?
Yes, they do, and not all of them are synthetic aperture radar, and that was the big name change. I don't know if you guys checked that sleight of hand that I had, and because we started as the Alaska SAR facility, I became director in 2002, and in 2003 I renamed us the Alaska Satellite Facility, and so. To kind of expand our horizons a little bit in terms of what we could do for NASA, that we wouldn't just be handling synthetic aperture radar data or synthetic aperture radar satellites, but our expertise, the people here really have expanded the world's knowledge of SAR data and how to use it. It's very complicated data. So the data center and the data work that we do is primarily in SAR, but the sensors, we're agnostic to the sensors, and we, depending on what kind of data is coming down, we handle it differently, and that's all driven by what NASA's priorities are.
Okay. Let's get to some viewer questions here. We'll start with one from Helen Howard. Helen would like to know, how do you use old data? Do you need old computers?
So that's a super good question. I love that. The only time you need the old computers to handle the old data is if you haven't migrated the data onto new media. So one of the things that, as a steward of data, that you constantly have to do is migrate data onto newer types of data storage. And so it's really the data storage media that limits what kind of computer you can use to read the data. So I think of it as painting the bridge, right? Say the Golden Gate Bridge, for example. They start painting it. They paint it until they get to the end, and by that time they need to start painting it again. That's what data migration is like. You're constantly migrating data. Because if those of you who have cassette tapes out there, you know that they're very brittle with time, and at some point they will stretch, and at some point they will break. So before that happens, you have to take those data and put them onto a different media so that you can use them on the newer computers.
So that's a great segue to a question I had. You've probably seen a lot of changes over the years, your many years. So maybe you could talk a bit about the pace of technological change with satellites. Is it pretty fast? Is it accelerating?
Well, So yes, I think that in terms of a lot of the technologies, it is accelerating quite quickly, depending on where in that you are. So we, for example, have had satellites that we've serviced for 11 years. And so however you're servicing those satellites, when they're still in operations, you have to continue with that. And if you do a migration, I think her name was Helen who asked the question, you have to make sure that you keep that capability, even if it means that going on to a newer computer, or in some cases, really nursing along those old computers to make sure that you can still do that work. But the data and how it's handled, the amount of data, and how fast we need to move it between who we here and the user community. All of that changes very, very rapidly. And I think it's still the hockey stick that we saw before. I mean, it goes along, and then all of a sudden there'll be a technology change or a paradigm shift that makes it just grow astronomically. Yeah.
All right, we've got several other questions here from viewers.
Okay.
This one from Jennifer Reynolds. Jennifer asks, with data volumes like that, how do you share it with scientists elsewhere?
So really good question. We have, believe it or not, we have those available for download. So it's not, it used to be that you would order something and we would process it and get it to you, sometimes shipping it to you on a cassette tape or a drive or any sort of media that we could do to ship it to you. But now it's downloadable. And so with the speeds that we have available to us today, we can make those data available to the science community 24/7. And you can download them. And depending on the data set, some data sets have restrictions on how to access it, and that depends on who owns the data. If it's U.S. owned NASA data, it's free and open distribution.
Worldwide?
Worldwide.
Wow. Okay. Question from Katan. Katan asks, I understand that you cannot map thermal regimes using SAR.
That's right.
With future advancements, would it be possible to obtain ground temperatures using SAR? Is it possible to combine temperature and SAR imagery?
So the last part of that's the easiest one. So yes, because when you take data from different sources, different types of data, you actually get more than the sum of the parts out of it. It's very, very useful and very informative to take multiple data sets and use them together. Always very interesting and sometimes surprising in what you find. And so that, yes. I don't know. I don't think so. And now I'm going to have to talk to Franz Meyer, the chief scientist, afterwards, and he'll be saying, why didn't you think that? Of course we could. I'm like, I don't know. So not to my knowledge, because of the type of energy that the radar is. It's really it's not going to be looking at thermal, but you can take that data and combine it with the thermal information that you have, and you can get more information out of that.
So how big are dishes on average that the satellite facility
So
operates?
the one on top of the roof is 10 meters, and the two that are in the woods are 11 meters-ish, 11.2, 10-ish. So, and then the one out in North Pole is there's also 11. And I didn't even mention, gosh, we have two other dishes that are 9 and 7 meter dishes that are university-owned assets. That's a whole other story. But so the four that I've been talking about are really the NASA-owned equipment that we operate for NASA. But the university has two large dishes out at the North Pole site as well.
All right, a couple other questions from viewers here. Maureen asks, is it possible to apply current SAR data to create a future projection or possible scenarios regarding climate change?
Oh, wow. I love these great questions. So not that I know, but boy, that would make an interesting thesis study. So I think what you can do, you would look for trends. So we have a lot of past data. I mean, we have all the original data. So you would be looking for trends in the data and looking for ways to project the continuation or an adjustment in those trends. It's a really good question. I like that question.
Another question for me, since I work here at the Geophysical Institute and see the big blue dish on top of the building every day. I notice it moves. How fast can it move, and how many people does it take to operate it?
Okay, so it can move a little faster than it does, but we purposely slow it down because we want it to last for a long time. So it's like a race car. If you drive it slower, it lasts longer, right? So when it's tracking a satellite, it goes from horizon to horizon in about 15 minutes. Okay, but in order to get set up for that, it has to get into position from wherever it is into the position to where the satellite is going to come, and it has to do that in just a couple of minutes. And so you will see it turn quite rapidly when it's getting into position to take a pass, and then it moves relatively slowly, but 15 minutes. So when you think about that, that's how long it takes a satellite at 500 miles above the Earth to go from one horizon to the next horizon. It's pretty fast.
And how many people?
Oh, how many people? We have it down in most. We have a lot of it automated, so we have it down to there's usually one person at least here at all times to make sure that we're getting all the data, and so there's the ground station has about I think 15 people that are responsible for that. So it's when you have to have someone here at all times, we're 24/7, 365. So Christmas Day, we'll be here. So.
All right, another question from viewers. Peter asks, what is the resolution of the SAR?
That depends on the instrument on the satellite, right? So it depends from satellite to satellite, but it can be down to 3 meters. So anywhere from 25 to 3 meters.
Okay, this one's kind of a funny question, and it's, okay.
Is it from you?
Yeah, it's from me.
Okay.
So when I see the dish pointing upward, I think of it like it's a cup, and so it's gathering all this snow. So what happens to that snow? We've had a lot of snow this year.
Yeah.
Do you clean it out with a broom?
No, we don't. No, but that'd be an interesting job, wouldn't it? So no, we use two different methods. We have heat tape, and we also use movement itself to keep it out. So when we have it up like that, it looks like a cup. We call that bird bath. So because it looks like a bird bath. But yeah, when it's snowing, we don't stow it in bird bath because we don't want all the snow to accumulate.
All right, here's a question from Rob. Rob asks, what is the lifespan of a satellite? What happens to the satellite when it is retired? And where is the backup or co-op location?
Okay, so I'm wondering if Rob means satellite or satellite dish. So because the age and the of them is different, right? So so let me just answer both. Satellites themselves, the ones that are on orbit, they're built to a certain nominal lifetime, and usually that's 3 to 5 years, and you always hope that it lasts its nominal lifetime at least. That being said, OCO, its lifetime was remarkably shorter than that because it launched and then it immediately fell out of orbit, and so it didn't take any data, right? That's a very short lifetime for a satellite. And then RadarSat 1 is a really good example. It lasted for 12 years. It was built for 3 and it lasted for 12. So satellites can vary. The dishes themselves, if you think about the antennas as being components that are mechanical versus components that are electrical, the computer parts and the electrical parts, that has a shorter lifetime. That has to be refreshed quite often. But the mechanical parts, and if they're taken care of well, which ASF takes very good care of the antennas with the proper maintenance schedules, et cetera, they can last 30, 40 years, so depends.
Excuse me. LJ asks, I understand when the old satellite on top of the building moved, people in the building could feel the building vibrate.
Right.
Does that still happen with the new one? And if not, what did they do to make that different?
So it's true, you could feel the old one moving, right? And moving the building, it was just, so people didn't notice earthquakes because you got so used to the building shaking a little bit. The main difference with the new one is the design of the pedestal, the part that is the vertical part that the bird bath sits on top of. The design is different, so it's more stable. So.
All right, viewers, we've got time for a couple of more questions here, so slip them in as soon as you think of them. What can we expect, this is from me, what can we expect in the years ahead with the satellite facility? What What are you looking ahead for? What do you see on the horizon, as it were?
Only good things. So, and actually that goes back to the third part of the last question about the co-op. So the co-op is here in the Geophysical Institute, and it's growing. And so the work that we're doing there is expanding. And we're pushing that technology right onto the edge. It's very, very exciting, the change detection work that's being done by the ASF teams here. It's very exciting. And as far as NASA goes, we're very much in a tight relationship with NASA in the synthetic aperture radar realm, and also in the looking at the ground systems as well. So I see a very bright future for ASF. We're growing. We started out in '91. They estimated that we would need 5 staff in order to run the Alaska SAR facility at that time. We now have 80 staff and growing at ASF, and it just gets more exciting. And as we bring in the students, the new technologies, it's just, I don't know, it's good stuff.
We're going to let LJ have another question here.
Okay.
LJ asked or says, I remember Dr. La Belle-Hamer telling a story that the GI wouldn't have the Alaska satellite facility if it hadn't turned out that the top floor of the building couldn't be used for staff.
No, I know what she's talking about.
Okay.
Yeah, so first of all, thank you for letting me tell a story twice, because my kids get very upset when I tell a story more than once. So I really appreciate you allowing me to tell this story again. So the reason why we have the dish on top of the LV building is because the LV building was designed to have an additional floor. And when they designed it, or when they started to build it, they ran out of money, so they cut one floor off, which meant that it was structurally sound enough that we could add all of the reinforcement that we needed to do up there in order to build the dish on top. So thank you, past Geophysical Institute, for not having that extra floor, because it allowed us to put a dish on top, and everything started with that dish on top.
All right, here's Rob with a question. Where is your back location for data collection if your dish would be unable to collect data?
Oh, good question. So if our dish is down, here's how I understand the question. The satellite goes over, it's trying to dump data, but it can't for some reason. We can't take it for some reason, and this does happen. Most of the satellites that we service now, most of them have onboard recorders, and so it's not imperative that they dump it at the very first station. They can actually wait until they get to another one. And so the reverse is also true. So we also get data here sometimes that was meant to go down in Norway, for example, or in other places, right? So the near space network, which is it's the grouping of all of the ground stations like ASF that work for NASA, we all work together and make sure that we are each other's backup.
Okay, last question, unless a viewer slips one in here while I'm reading this one. Last question, and this is kind of, it's for me, it's a good sum up question. It's, what do you find most rewarding or interesting about your work in SAR? You've done it for a long time.
I have done it for a long time. So, and I have to pick just one thing.
No, you can say more than one thing.
Okay, so to me, there's 2 integrated things that make coming to work every day a blast. And one is the science itself. I truly am a scientist. I tell people I'm a scientist first, and then I got my degrees. I didn't become a scientist because I have a PhD. I got a PhD because I am a scientist. So I really do enjoy it, and I do think equations are beautiful and all of that stuff. And I get very excited about us being able to push knowledge and help people with our data. But in the end, every day we spend more time with the people we work with than the people in our family. And For me, the people here make it all worthwhile. I love to come to work because I love the people. So, two things.
All right, Vice Chancellor, thank you so much. It's a great presentation to wrap up our series with. And okay, viewers, I'm going to pop back up on stage here, and I'm going to hand out some prizes and have kind of a wrap-up statement for the series here, all right?